All right, it's my pleasure to introduce the next speaker, Shinji Watanabe. So when we were going to start organizing SANE this year, John, Jonathan, and I, we haven't even invited any of the speakers. We were thinking like who to invite, and there's this question: who's the most active speech researcher right now? And I think all three of us agreed that it's Shinji. So Shinji has a long career. He got his PhD from Waseda University in Tokyo, had been in NTT in Kyoto.
Yes.
Then for half of the last decade was in Cambridge and Merle. Then went to Johns Hopkins in Baltimore, and for the last couple of years is in Carnegie Mellon in Pittsburgh. So let's hear from Shinji.
Okay, thank you, Anab. So today's talk is about explainable end-to-end neural network for field conversation recognition. And let me start from a little bit of big picture of what I and other researchers are actually targeting for speech problem. So which is understanding all kind of auditory scene with machine. So we can have a lot of the mix of the various sound source in our environment, right? So we want to recognize everything, recognize everything. That will be our kind of one of the goal. And one of the important aspect in the speech researcher in this machine listening context is to the targeting to understand all the kind of environment from the audio, like who is speaking when, what, where, how, why, and so on. So this research, I am actually talking about this one of the ultimate goal of speech and audio processing, but just a part of them. And we are still far from understanding everything. But I just want to explain about our kind of a trial for this kind of a problem. And this is today's talk. First, I will talk about the end-to-end automatic speech recognition, which Tara already explained. But I will explain about one of the different view of how to solving this problem. And then talking about the speech recognition and the speech enhancement unification as an example of the machine listening problem. So first, as Tara also mentioned, speech recognition was developed with a pipeline system and now moving to the end-to-end system. This has a lot of benefit. Like, for example, we can directly mapping the speech signal to the text information. And as Tara mentioned, the simplification is actually additional quite important benefit. And the last part, integrating the various architecture with the single computational graph. And then we can actually optimizing the entire neural network. That is also another benefit, I would say. However, these the characteristics actually can be a pros and cons. For example, first part, directly mapping the speech signal to text is very great, but we don't know what's happening inside, right? And also last part, integration with the entire neural network optimization, making the optimization sometimes very difficult. So always this kind of things has pros and cons. And in my talk, yes, I still want to work on the end-to-end neural network. However, instead of tackling the black box approach, this talk, I will try to tackle this the neural network, end-to-end neural network, as a transparent box, which means that we maintain the modularity, and we also try to kind of making the computational graph still connected, so that we can also back propagate everything. And the important part in this talk is the explainability. So I will explain this kind of concept in the following several kind of applications. Okay, so first I will talk about Farfield speech recognition, which is actually quite important for us to make the application bigger from the crosstalk microphone setup to the more like understanding human communication or human-robot communication and so on. And this is actually one of the part of the machine listening problem, I would say. And this is just the distance is far from the microphone and the source, but it's actually coming a lot of difficulty. Like for example, due to the kind of far distance makes the kind of SNR the worse, and then we can capture the background noise. We also have an interference speaker, and also reverberation and so on. So Farfield speech processing is actually quite a complicated problem. However, we actually can somehow solving this problem by using the smart speaker techniques. And I will explain about what kind of technology are needed to solving this kind of Farfield speech processing problem. One of the important components is speech enhancement. And there are several types of the speech enhancement problem. One of them is denoising.
Where else in the third world is there so much energy and progress as in China? Where else in the third world is there so much energy and progress as in China?
The other problem is dereverberation.
Uncertainty concerning the proposed acquisition of A.H. Robbins by American Home Products helped push both stocks down. Uncertainty concerning the proposed acquisition of A.H. Robbins by American.
And the other is separation, which Scott is already explained.
The United
Some
States
critics,
undertook to defend Western
including
Europe
high
against
Reagan
Soviet attack.
administration officials, are raising the alarm.
The United States undertook to defend Western Europe against Soviet attack.
Some critics, including high Reagan administration officials, are raising.
Okay, or by the way, deep learning based method. So we can actually enhance this kind of technology by using single channel microphone to multi-channel microphone. And then in this situation, we can actually make a spatial beam and then localize the source sound. So that is actually powerful. And this can be applying to the not only for denoising, but all speech enhancement scenario and so on. This is our current technology. Our successful smart speaker application was based on the combination of the signal processing technology and the machine learning. And in this talk, yes, I will talk about speech recognition for Farfield setup. Here, usually we put the multi-channel speech enhancement component in the front end, or even dereverberation and so on. And how to tackle this one? We will use an end-to-end neural network. One approach is definitely considered to work on it as a black box approaches. But this approach, this talk, I will also explain about the explainable neural network, which keep the original modularity and carefully design each module to keep the computational graph. And then we can also provide him the interpretation. So this is our kind of a philosophy of solving this kind of problem. And from now on, I will introduce several my prior studies or current study, but I just want to mention that this area is now quite largely studied, and a lot of studies happened. So I cannot fully cover many of the research groups' work, but if you want to know, you guys also check our ICAS tutorial last year. Okay, first problem is to jointly solving speech recognition, denoising, and the dereverberation. And let me start from a little bit old work, 2017, because this is a very important concept we made. And it's actually we have done when I was at tomorrow. And some of the actually colleagues here actually working together with this problem. So in this the problem, we actually try to combine speech enhancement and speech recognition in a single neural network. And at that time, we use a mask-based neural beamformer and attention-based encoder-decoder network. And goes more quick detail about our kind of front-end architecture. So this is actually like that. I did not fully explain the detail, just for the simplicity. But as you can see, this diagram looks like some array processing, right? It looks like a kind of signal processing, the block diagram. Actually, what we have done is that try to imitate beamforming network. We call it beamformer sum network. And we actually imitate famous minimum variance distortion response at a beamformer, MVDR. And again, I did not explain detail about the equations, but this the MVDR is actually written by, for example, the multiplication of the vectors. And this filter is estimated by the matrix inverse, trace, multiplication, and weighted sum, and so on. So actually, all the kind of components are based on the fundamental, the basic math. So we actually can get the derivative of all this kind of neural network. So this is our kind of first approach of combining beamforming and speech recognition with a single neural network. How to train it? Of course, one way is to prepare the noisy and clean speech and the back propagation to obtain the speech enhancement model. And we can also train the speech recognition model based on the back propagation, and then we can combine it. However, in this framework, we actually don't need an intermediate clean speech. We could actually train speech enhancement and speech recognition by only using speech recognition criteria. This is actually one of our concepts. We try to kind of show that. And with that, we actually don't need pair clean and the noisy speech. And then we can realize this kind of the training of the enhancement and the speech recognition at the same time. And actually, after we made this kind of technique, we further extended it to also include the dereverberation and so on. And then similarly, we make a dereverberation and back propagate all the kind of a neural network. In this case, we also imitate the famous weighted prediction error based on the dereverberation. And again, I kind of skip the explanation of the equation, but as you can see that many of the equations are actually that we can easily get the derivative, so that we can actually get this back propagation working by combining the reverberation, beamforming, speech recognition, and so on. And again, note that we did not providing the intermediate clean speech information. Okay, let's move to the experimental result. So as you can see, basic end-to-end baseline without using any enhancement, it's a kind of very bad result. However, by using the dereverberation of beamforming, state-of-the-art dereverberation of beamforming techniques in the array processing, we actually get a very good performance. Again, this is the power of the signal processing. And the last one is our approaches. Actually, we also imitating this kind of a network, but this is actually single neural network, and then obtain comparable performance and so on. And usually speech recognition researchers finish their kind of a research only with a word error rate, but this one has actually byproduct. Again, our neural network is designed to make the speech enhancement to be working. So actually, even this neural network, we only feeding the speech and corresponding transcription and getting the transcription to be better. This enhancement part can be working to be enhanced the speech or not. So this is actually quite an interesting problem. And this approach is completely different from the black box approach. Black box approach, we cannot interpret what's happening inside, right? But by using this kind of approaches, we can actually provide the meaning of the intermediate representation, again, since we imitate this speech enhancement part. So this is actually spectrogram, and also let's listen to the audio.
GM's share of the total car market fell to 35.6% from 39.2%. GM's share of the total car market fell to 35.6% from 39.2%.
So can you guys recognize it's denoised, right? Again, I didn't ask them to clean the speech. I asked this neural network to get a better ASR performance. But thanks to this modular network, we can actually realize speech enhancement and the speech recognition at the same time. So this is the power of using the modular-based approach, explainable neural network. And this approach is fully based on the signal processing motivated architecture. And then I often got the question. First, as I mentioned, I only feeding the noisy speech and the corresponding text to ask the neural network to be better. Of course, that I using always flat start, but why do you stick to the flat start? Of course, I want to showing that, this kind of a concept so that I kind of using the flat start. And the other question is, is this really reaching the state of the art? That also often I was asked. And then, I kind of usually explain that, no, this is the academic research and, the want to showing the concept and so on. This is so-called academic excuse. And, but in this the situation, I also try to make it further improve by using various state-of-the-art technique. So this is actually our latest the technique. Why not combining it to a strong self-supervised learning model? And why not using the pre-training model? And why not using multitask learning? Since sometimes we can also get a clean speech, right? So we actually also, in addition to the previous method, we actually make everything. We actually using the self-supervised learning. And of course, which is the pre-trained for each of the components in advance. And finally, we fine-tune this model. And also sometimes we can actually get the simulation data to get the clean data, right? In this case, we also using the multitask learning. However, in noisy cases, we only using this cross entropy based training. And this is the result. So these are the chime 4 and reverb challenge benchmark. And first look at chime 4 data, and our approach is actually getting the best performance. Second one, reverb challenge. We also get the best performance. We actually update the best performance in both chime 4 and reverb benchmark. However, I just want to mention that this is using the external data. So I would say that this is more like showing the upper limit of what we can do if we using various techniques. But still impressive to me because the word error rate is actually goes to almost 1%. And all these tasks are actually the equivalent in terms of the speaking style to the Wall Street Journal. So we can have actually upper limit in the clean speech, which is around 1.5% word error rate. So this means that this method getting the almost same as the clean speech performance. And it may be overly, I would say, but with this result in our lab, we thought that the single speaker noisy problem is almost solved. And then we should move to the multi-speaker problem. So that is kind of our kind of situation. And maybe I can also play the audio of these approaches.
There shouldn't be any risk to the banks in this sort of stuff, said Lawrence Cohn, a banking analyst at Merrill Lynch. There shouldn't be any risk to the banks in this sort of stuff, said Lawrence Cohn, a banking analyst at Merrill Lynch.
Yeah, similarly, slightly reducing the speech enhancement and then getting a quite good performance in terms of speech recognition and so on. So again, this is the concept of our approaches. By keeping the modularity, we can actually keeping the performance and also providing the explainability. And the rest of the work, I basically applying this concept to the other speech enhancement problem, like a separation and localization and so on. So I will do not explain the details so much and quickly go through, but I hope you guys understand this methodology. So similarly, speech recognition pipeline is like that. And the multi-speaker speech recognition pipeline, if we try to incorporate, we have a speech separation in the front end. And we can actually consider deal with the multi-speaker speech recognition. If you have a multi-channel, we can have a speech separation and the multi-channel speech enhancement, and then having the ASR is following. And the target is to make this problem to be solved by end-to-end neural network. One way is using the black box neural network. And the other way is using the explainable neural network. And this work is actually extension of the previous approaches, but using the separation in the beginning and the beamforming to define the speech separation and so on. And also training part, we're using a permutation invariant training in the reference level, which Scott already explained, but the Scott's case is signal level, and we applying it to the reference level. And the beamforming subnetwork is we again using the MBDR, so it's almost same. But we actually now have a multi-speaker cases, so speaker index is actually added. And then we make this kind of all neural network to be differentiable, one single computational graph, so that we can back propagate all the kind of network. And since this one is multi-channel input and the multi-speaker output problem, so we call it MIMO speech. And later, we also extended to deal with the recent advance in the beamforming and the dereverberation techniques. Recently, the people actually started to jointly solving dereverberation and the beamforming. And there are a lot of progress in this field. And one of the approach is the weighted MPDR. So we actually using this neural beamformer, which again consider the both dereverberation and the beamforming, and then they back propagate all the kind of neural network based on these approaches. And this is the speech recognition result similar to the previous cases. With just a single channel cases, we have some kind of OK result. And this, the beamforming is actually improve the performance. This one is the still pipeline using the independent NVIDIA beamformer. But by combining all the kind of neural network, we can get a further improvement and so on. And similarly, we can show you our explainability, which in these cases, we can extract a separate signal from here. Black box approaches, this can be just the continuous hidden vector. But we imitated this kind of neural network, so we can actually extract the separated signal. Let's listen to that.
South Africa, The Solution by Francis Kendall and Leon Lowe has sold over 25,000 copies since last year. South Africa, The Solution by Francis Kendall and Leon Lowe has sold over 25,000 copies since last year.
Although those gains eroded during the afternoon, stock prices stayed within a narrow range until the last half hour of trading.
So similarly, only by using the ASR objective, we can actually making this neural network to be solving the separation and the ASR at the same time, and also keeping the explainability. So basically, this concept is applied to the other problem. Another application is speech, speaker localization, and so on. And they're almost same the presentation style. We have a speech recognition pipeline. How to solve the multi-channel multi-speaker problem. We already showing that speech separation and the multi-channel speech enhancement front end is important. And if we also having a localization explicit information, we can actually solving the speech recognition separation and localization at the same time. And how to solve it in a single neural network. One approach is a black box approach. And our approach is explainable neural network and so on. And then here, we actually attaching the localization neural network. And then later, speech separation based on the localization information. NVDR beamforming, and multi-speaker speech recognition is following. And again, all are single neural network. And I skip the detail about the localization subnetwork. And this is a kind of result. The first one is more like an explainable part. Actually, this neural network is also only trained to the ASR criteria, based on the ASR criteria. But we can actually get the performance better than classical music-based localization-based approaches. This is the L1 angular error, so lower is better. And also in these cases, we can even improve the performance from the previous MIMO speech and so on. So basically same, the explainable neural network can also providing the information of where. So this is our current the state of our kind of directions. And we actually also want to further integrate other problems, and some of them are ongoing, and some of them are actually we want to expand, and we really want to collaborate with you guys to solving this kind of problem by integrating everything. So far I mentioned that only good things. However, as I mentioned, all kind of problem is actually pros and cons, right? And this is what I already mentioned. By using the neural network, we can directly getting from speech to text signal. However, we don't know what's happening, and we lost explainability. However, explainable neural network can actually recover explainability. Very cool. And the third one, difficult to optimize. Well, it depends on the difficulty. Some people may say the single neural network might be easy to optimize. But anyway, our kind of experience, this the modular-based neural network is easy to optimize, easy to debug, because we can easily get the meaningful intermediate result. For example, this part, we can just ask the listening, oh, this is not audio. This means that this is not working as a speech enhancement. Gradient does not go to this area, so that we can debug it or something like that. Explainable neural network actually can make the debug easier. Again, sounds like good thing. However, explainable neural network actually makes another issue, which is very complicated. Again, it becomes like a previous the modular-based approaches. I will make the font bigger. Again, you know, I should be humble. So, and this part is actually quite difficult. So I am still trying to find a way to how to make this explainable neural network, modular-based neural network, to be simple. However, one of the kind of approach we are also working is, yes, this is difficult, this is complicated, but maybe providing the open source and then making it at least reproducible. That is another our kind of other group's strategy. So last, I will introduce about the our group's activity for open source. So as I said, speech enhancement problem is various kind of factors reducing the distortion from the original signal and so on. And we actually have been working on this area, especially for pushing the open source direction. First one is the 2020 effort. We actually maintain the open source toolkit called ESPNet, and we actually extend the speech enhancement part. So we call it ESPNet SE. And we later actually extended this one to further put a lot of effort for this open source toolkit. And this is actually the this year interspeech paper. So anyway, we actually put a lot of the implementation, and now the recipe example covering 20 the famous speech enhancement tasks, and we have 12 single channel models, speech the separation enhancement models, including the mixed that Scott explained. multi-channel model, we actually put a lot of emphasis because multi-channel speech enhancement usually get a quite good improvement for the downstream tasks. And the downstream tasks, initially we only focus on the speech recognition, but now we also supporting the speech translation and the spoken language understanding and so on. And not only just the making the kind of a wide variety of the tools, we actually try to make this to be state of the art. This is one of the our recent result, the ICAS Grand Challenge on the L3DS 2022 challenge. And based on this kind of ESPNet speech enhancement toolkit, we actually won the first place among 17 other submissions. And the second example is a TF GridNet. This is actually the getting the best performance in the Wall Street Journal 2 mixture. This is a little bit the toy problem, but still good to showing the concept of whether speech separation is working or not. And actually, as you can see that compared with the previous all result, ours are actually some margin to improve the performance. By the way, one more message is that this one is time frequency based approaches. So we are actually revisiting the time frequency based approaches and found that it is powerful and also quite simple. So this is a main component of the ESPNet speech enhancement the project. Basically, we providing the independent enhancement module, including a denoising, dereverberation, separation, and single channel and multi-channel. However, as I mentioned, I want to also providing the reproducibility of my previous talk. So we are actually caring about making this speech enhancement component to be fully differentiable so that it can be combined with the other downstream tasks like a speech recognition, spoken language understanding, speech translation, and so on. By doing that, we can realize a cocktail party effect by machine. That is our kind of our goal. Seems like I finished a bit earlier, but it can be fine, right? Yes. Yes. Okay, so let me summarize my talk. Today, I explained about the end-to-end speech recognition, end-to-end neural modeling, and focus on the integration. And the speech recognition and the speech enhancement integration that we use as an example, because then we can solve the Farfield speech recognition problem, speech processing problem. This is very nice. This is tight integration, and we can theoretically possibly get the global optimum. And there are a lot of ways to do it, but in our approach, we actually using the explainable neural network by maintaining the modularity. And again, I have to admit that it makes a kind of a neural network complicated, but we try to make the open source activities to make this kind of problem to be reproducible and so on. What is future direction? Of course, we should also having a more machine listening functions and having a more tight integration with NLP data and so on. And the other direction is more realistic data. I would say that time for the reverb real data. However, it is a little bit simple problem because it is a real recording, but read speech and so on. So we are actually working on more realistic data. One of the example is a Chime 6 challenge, which some of you may know here. This is a really hard everyday conversation scenario, and one of the most difficult speech recognition tasks. And we actually using this tackling this problem right now based on these kind of the techniques. And this is, by the way, first the beginning of the challenge. Word error rate is 73.7. This is not accuracy. This is the very, very difficult task. But after the challenge, that we actually using the 2 challenges for this same data. And now we are getting around 30% in the challenge-based system. However, by using the previous techniques I have explained, we actually already got a slightly better performance. And we are now working on summarizing it to the ICASP. Okay, so that is my talk. Thank you so much.
Thanks for that, Shinji. Questions, anything? When you're optimizing the beamformer and the denoiser together with ASR using the word error rate criterion, it probably has a good potential for improving the intelligibility of that mean speech, which would be highly valued by the forensic community. My question is whether it also is more prone to hallucination of words. So when the ASR is making a word error mistake, how does the clean speech look in this case? Was there any analysis of whether hallucination is happening more when you're dealing with
frankly, I don't have such kind of analysis. Maybe good to look at this. But my experience, if this happens, this can be mitigated if we using the separated optimization, right? But in these cases, the separated optimization and the joint optimization performance is actually quite similar or sometimes better. So in some closed scenario, in some kind of the designed scenario, it seems like such kind of things does not happen. But of course, I think your question would be more robust. For example, open cases, this may happen, right? So yeah, I don't have a clear answer about it. Yeah.
Thanks for the very inspiring talk. So actually, I have a question about, so in the third part, you show like you can try to combine the speech enhancement with like the self-supervised feature structure.
Yeah.
And then follow by that. And so I'm curious, like, so for this self-supervised trend feature structure, it like usually is more robust than OSR system. It is exposed more data, right?
Yep.
So I'm wondering specifically in that condition, have you compared like the speech enhancement module outputs to see if, say, you pair that with the self-supervised feature, you probably don't have to implement the speech that much, right? So have you compared the ratio?
Yes. Yes, actually, you are right. Since the self-supervised learning model is very strong, so I don't prepare the number, but anyway, our paper, we have such kind of aberration studies. Yes, this system, the most the dominant performance improvement comes from the self-supervised learning, which as far as I remember, it goes the error rate from the up to like 4% or something like that. But the rest of the kind of the reduction, like the half of the reduction, actually comes from the enhancement. So still enhancement is kind of important to getting the kind of performance to be close to the clean the signal performance.
In terms of output is like now here than the like first version of the model.
Yeah, that may happen actually. Yeah, that may happen. Anyway, the many big improvement comes from this self-supervised learning model. Yes.
I guess you could train without the supervised learning features first, and then maybe to pre-train the enhancement layers on a more stricter feature extractor that needs cleaner features, and then switch to a self-supervised learning feature to get the benefit, to like force it to really do better enhancement first, and then you can
definitely, yeah, definitely, yeah.
Thank you. So in part 2 of the talk, you showed all the systems and metrics, loss functions.
Yep.
I'm wondering, do you think you will get more gains on the result by providing the targets such as speed limitations?
Yeah. Actually, one of the results I have shown is not the near field result, but it comes from the result of using the pair data of noisy and the clean speech. So in the this kind of best performance result is actually using the intermediate target as a pre-training stage, or even during the fine-tuning stage, we're using the multitask learning. But just want to mention that this work is just to get the best performance. To get the best performance, we can do this kind of a complicated other recipes. And the main message, one of the main message is that the flat start is also working.
Further question with that.
Thank you so much for this. Actually, a couple of questions, but one, I would say that the idea is really, really good. It's like patching levels together, but as we patch more tasks towards the end, like right now it's going on. So eventually we get a spread, but as we patch more complex tasks towards the end, how do we expect the performance of each specific part to change? Like, does as the task gets contaminated, like with more and more stage, does each stage get better results? And also, if you contaminate more tasks, and for each specific task, it's more prone to, like, so the error also creates that problem. And if we are planning to introduce more material into this, then contamination of more than 6 stages of the right is inevitable.
Yeah, actually, this is a very good question. And I would rephrase this one is more like a fundamental question of the modular-based approach versus black box, not say that the entire neural network based approaches. Again, everything has a pros and cons. And one of the issue of the modular-based approach is that anyway, mapping the information to the explainable representation. So this is actually fundamental problem of the modular-based approaches, I would say. We actually making this part to be interpretable, right? Which is very cool. But this means that this actually rich information in the noisy multi-channel rich information is projected to the single channel, the clean speech information, right? So this means that for this specific task, like a speech recognition, we actually can keep this the information and then getting the performance better. However, if we try to understanding everything, for example, the noise information or room impulse response information is in some cases very important, right? However, modular-based approaches mapping this information to the kind of limited space due to the interpretability. And this actually happens if we further performing the modular-based approaches. For example, one of the another possibility is to introducing the phoneme, which is very great. If we have our, such kind of resources, we should definitely use that. However, this means that we kind of mapping the information of the rich speech information to only in the phoneme. And then from phoneme to try to recover the language information and so on. So basically, modular-based approach has this kind of the issue. Thanks to the explainability, it becomes tractable, but at the same time, it actually has a bottleneck in terms of the information. Of course, residual connection and so on can, solve this kind of issue, but in general, this is another kind of issue of the modular-based approaches, I would say. So if your question, for example, if we have a more modular system and so on, probably easy to debug, but it's, as you mentioned, it's easy to stuck to some kind of the local optimum. Again, since we lose the information due to the explainability. So that is my actually answer. So this is actually very high level the problem, or I would say the concept of the modular versus a single end-to-end neural network problem.
All right, I think we should stop here. And thank Shinji again.
Thank you so much.